If you want a function like add2, that's obvious enough. You don't have to know about the encoding of numbers. You can just use add1 twice and so on for add3. But what if you want an add function in general? So add takes two arguments, n and m, and it's supposed to return a number that is n plus m. Now, of course, if we knew what m was going to be, we could write out the right number of add1s here. But just like we saw with add1, we don't know what m is. It's going to be passed in later. On the other hand, just like we saw with add1, we can take advantage of the encoding of m because we're implementing this basic operation like add for numbers. And we know that the encoding of m is that it applies a function m times. So we can give m add 1, and it will add 1 to n m times, which of course is the same thing as m plus n. Again, you could try it real fast. We could try adding 1 and 2. That's going to be the same as 2 applied to add 1 of 1. 2 will use add 1 twice on 1, so we get add 1 of 1. And because we've already seen that add 1 does the right thing, we expect to get 3 from that. And we could work out all the details if we had to confirm that this is how add works. So add, again, is taking advantage of the representation of numbers in order to implement addition, just like you do with basic operations. How about multiplication? To multiply n times m, one way to think about that is to start with 0 and then add into it m times. And we've seen this kind of pattern before. Because our add function is curried, it takes one argument at a time, we see that we really have an add n function that we're using m times. So we can do a similar thing as we've done before. We pass add n to m, so m times we will add into 0, and that will of course multiply for us. Besides adding and multiplying numbers, we might want to check whether a number is 0 or not. Is 0 is different than add and multiply in that it returns a boolean instead of a number. So we're just going to use the boolean encodings that we already have, true and false. But how do we pick one of those based on whether n is 0 or not? Well, 0 is different from all other number encodings in that it ignores the first function that we pass it. Right? If we take this function and apply it 0 times to true, then we'll get true back, but 1 or more times back, we'll get false. So that's how we can distinguish 0. Just to write this all out, if we pass 0 into is 0, that means we 0 times apply lambda x false to true, which means we just get true back. But if we pass is 0, 1, then when we use 1 on this function in true, that means we will 1 time call this function on true, which means the true goes in for x and we get false back. You may notice if we do is 0 of 1,000, then we will end up doing 1,000 function calls to get a false back. So it's not necessarily very efficient, but again, we're just showing that encodings are possible. What about going back past 0 into negative territory? How can we implement sub1? So sub1 is like add1 in that it takes a number and it returns another number, which is, of course, is a function that takes f and x. But we can't apply the same trick that we used for add1. Remember, in that case, we took n and applied it to f and x, and that gave us n applications of f. But this time we want n minus 1 applications. So if we try this trick, we've already gone too far. There's no way to undo a call to f to get to n minus 1 calls. So the new trick we need is to use pairs and keep track of 2 numbers at a time. So in general, I'm going to have a pair that has an old value and then the next value. And that way, if I build up to n here, I can look back at the first part of the pair, and get the n minus 1 out. To get started, we'll start with 0 and 0, but after we go at least one spot, then the number that's the second part of the pair will always be 1 bigger. So I need this helper function that I'll call shift. Shift takes our current pair, which has n minus 1 and n. It shifts the second part, that is, it moves the n to the first part of the pair and adds 1 to the second part of the pair. So if we start out at 0, 0 and we shift it once, then we get to 0, 1. If we shift that again, we get to 1, 2. And in general, when we shift a pair n minus 2, n minus 1, we get to pair n minus 1, n. And so that means if we start out with 0, 0, and we apply shift n times, that means we will end up with n minus 1 and n, so we just want the n minus 1 part there. You could apply sub1 to 2 and make sure that you get a 1 back to double check. And of course, using the same trick that we used to get from add 1 to addition, you can go from sub 1 to subtraction. Now notice if you pass a 0 into sub 1, it'll just give you a 0 back. So having subtraction doesn't mean that we get to negative numbers. We only get operations that stay within the natural numbers.